Hello students, welcome back. Today we'll continue with the miscellaneous exercise of chapter number 1, that is relations and functions. Okay, let's start with question number 1. F R to R is defined as fx is equal to 10x plus 7. F of x, that is equal to 10x plus 7. Find the function g r to r such that g o f equal to f o g equal to I r. That is identity function. Okay, so it is given that g o f equal to f o g, that is equal to identity function on R. So we have to find out such function. Clear? So that FOG equal to GOF, and that is equal to IR. That is identity function. Okay, now so identity function. If a function is identity function, then if f is identity function, then fx will be equal to x. Here fog and gof are identity function, right? So I will write it down. Fog of x, that is equal to identity function, that is equal to x. Okay, so when I will solve it, f of g of x is equal to x. Okay, now see here, we will take this function f, we will solve it f. See, f of x 10x plus 7. So we will assume this as x. So it will be 10, instead of x I am putting bracket, plus 7, that is equal to x. See, here it was x. Here is gx, g of x. Okay, so 10 of g of x is equal to x minus 7. So g of x is x minus 7 upon 10. So this is our answer. So the function g r to r will be g of x equal to x minus 7 by 10, such that fog will be equal to g of f is equal to I r. There you can also verify it. See, if you want to verify it, like fog of x, this will be equal to f of g of x. Now what g of x we found out? X minus 7 by 10. Okay, what is f of x? That is 10x plus 7. So 10 into x minus 7 by 10 plus 7. 10 gets cancelled. X minus 7 plus 7, that is equal to x, identity function. Similarly, let's see GOF of x, that will be equal to G of f of x. So G, what is fx? 10x plus 7. Now what is gx? X minus 7 by 10. So instead of x, 10x plus 7 minus 7 by 10. So 10x plus 7 minus 7, 7 gets cancelled. 10x by x, that is equal to x. See, fogx equal to x, gof of x equal to x. Both are same, and as we are getting x, so it is also identity function. Here, so this is our answer. Verification is optional. Okay, you may do, you may not do it. Clear? So this was about question number 1. So just note it down. Now let's move to the next. Question 2. Let f from w to w be defined as fn equal to n minus 1 if n is odd and fn equal to n plus 1 if n is even. You have to show that f is invertible and find the inverse of f. Here w is the set of all whole numbers, means the domain and codomain, they are whole numbers. Okay, now see, here I will split the function into two parts. F of n, this will be equal to n minus 1 if n is odd, and n plus 1 if n is even, right? So now say we have to prove that it is invertible. So for that we need to prove it is 1 1 and on 2. So first let's begin whether for 1 1. Okay, now let's take n m belongs to whole number and n and m are odd. Okay, now let f of n equal to f of m. Okay, so when it is odd, I will use n minus 1 equal to m minus 1. That implies n is equal to m. This is case 1 when both are odd. See, we got n equal to m, fn equal to fm, that implies n equal to m, therefore it is 1 1 for this case. Case 2, n m belongs to w. Now let's take n and m are even. Okay, now let f of n equal to f of n. When it is even, we use function n plus 1. That means n plus 1 equal to m plus 1. 1 1 gets cancelled. So n is equal to m. Again, see, when both are even, we took fn equal to fm. That implied n equal to m. Hence, in this case also it is 1 1. Now let's take case 3. We need to take all the cases. Okay, case 3. N m belongs to whole number, but n is odd and m is even. Now see, n is odd and m is even. That implies n cannot be equal to m. N is not equal to m. Here, so let's take that fn equal to fm. Is it possible that for two different number fn equal to fm? If it is yes, that means it is not 1 1. If it is not, then it will be 1 1. So fn equal to m. Now what is n? Fn n minus 1. And what is fm? M, it is even, so m plus 1. Now n is odd. If we subtract 1 from odd number, that will be even. If we add 1 to even number, because m we have taken even, that will be odd. Is it possible that even number is equal to odd number? Okay, that is not possible. Okay, so our assumption is wrong. Is wrong. What we assume? We assume fn equal to fm. That implies fn is not equal to fm, right? So see, if fn is equal to fm, we proved that in both the cases n is equal to m, right? And if n is not equal to m, that means definitely fn will be not equal to fm. So from all these three cases, okay, let me write down this as 1, 2, and 3, right? From 1, 2, and 3, f is 1 1 function. Clear? Okay. Now let's see for onto. Okay, for onto, if the range is equal to codomain, then it will be onto function. So let's see what we are taking x and what we get. Let's take what we take n and what we get fn. Now whole number, so I can take 0, 1, 2, 3, 4, 5, and so on. Now 0, so 0 we will consider even. So it is even, 0 plus 1, 1. 1, that is odd. Clear? So 1 minus 1, 0. 2, 2 is even, 2 plus 1, 3. 3 is odd, 3 minus 1, 2. Okay, 5, 4. So see, you will see here you will get 0, 1, 2, 3, 4, 5, and it will continue. That means you will get all the whole numbers. So this is the range. So it's clear that range of function is equal to codomain, right? That is whole number. Hence, it is onto function. It is 1 1 and it is onto, that implies that f is invertible. right? F is invertible. Clear? So we have proved that F is invertible. Okay, now we also need to find out F inverse. We also need to find F inverse. Okay, so see, for that, what we will do? Okay, let's take f of n equal to, see, it is given f of n equal to n minus 1 when it is odd, and f of n equal to n plus 1 when it is even. Okay, so first case 1, n is odd, so fn, let's take this is equal to y. What is fn? N minus 1 when it is odd, y, so that implies n is equal to 1 plus y. Here n is equal to 1 plus y. Okay, so when n is odd, the inverse will be 1 plus y. And what is 1 plus y? N is odd, that implies 1 plus y, that will be equal to odd. So that implies y is even. Clear? Because clear cut it is given that n is odd. So if we add here 1 plus y will be odd, and that implies y will be even. Okay. Now let's take case 2 where n is even. Case 2, n is even. So f of n will be equal to y. Now when n is even, what was our f of n? You can see here n plus 1. So what I will write down? N plus 1 equal to y. That implies n is equal to y minus 1. Okay. Now say in this case n is even. That implies y minus 1 is even. And y minus 1 is even. That means y is odd. Yeah. So this will be inverse in the case n is even, or in the case y is odd. Okay. So what I can write it down, f inverse. Okay, I am writing f inverse y, that is equal to y plus 1. Okay, when y plus 1, when y is even, see I am using this when I got y is even. Okay, y is even, and y minus 1 when y, see I got y here odd. Okay, or else I can write it down in this way, f inverse n equal to m plus 1 when n is even, n minus 1 when n is odd. Okay, see, you can confirm it, okay. See how to confirm. Let's take 2. What is f of 2? What is f of 2? Okay, f of 2 I got 3. So now f inverse 3. Okay, now see, I should get 2. Now f inverse 3. 3 is odd. So when 3 is odd, which function I need to use? N minus 1. So 3 minus 1 equal to 2. Similarly, let's take f of 3. What I got f of 3? 2. So f inverse 2, it must be 3. Right? So when here 2 is even. So for n is even, for inverse is n plus 1. 2 plus 1 equal to 3, right? So this shows me that I am correct. Okay, so this was about inverse function. Clear? So just note it down. Okay, now let's move to the next one. Third, if f r to r is defined as fx equal to x square minus 3x plus 2, we have to find out f of x. Okay, so first let's write down what is f of x. X square minus 3x plus 2. Okay, now I need to find it out. f of x. So this will be equal to f of, let's put instead of fx, x square minus 3x plus 2. Clear? Now again f. So I will use this function, instead of x I will put bracket. I will put larger bracket equivalent to this size, minus 3x plus 2. Okay, so now I will put this x square minus 3x plus 2, x square minus 3x plus 2. Instead of this x, I replace it by this x square minus 3x plus 2. Okay, so now what is a plus b plus c whole square? A square plus b square plus c square plus 2ab plus 2bc plus 2ca. So this will be a, this is a, so x square whole square plus b square. What is b? Minus 3x. C, what is c? 2 square plus 2ab, 2 into x square into minus 3x plus 2bc, 2 into minus 3x into 2 plus 2ac, 2 into x square into 2 minus 3 into x square, 3x square minus 3 into 3 minus minus plus 9x plus minus, sorry, minus 3 into plus 2 minus 6 plus 2. Okay, so this will be x square square x raised to 4 minus 3x whole square, 9x square, 2 square 4, 2 into x square into minus 3x, it will be minus 6x cube. 2 into 3 into 2 and minus, so minus 12 and x plus 2 into x square into 2, 4x square minus 3x square plus 9x minus 6 plus 2. Okay, so first let's take x raised to 4, there is only one term, so this will be equal to x raised to 4. Let's take x square, 9x square, 4x square minus 3x square. Okay, so 9x square plus 4x square, that is 13x square minus 3x square, 10x square, so plus 10x square. Okay, now let's take about the constant term, 4, 6 minus 6 2, 4 minus 6 minus 2 plus 2 0. Now x cube, 6x cube. Okay, only one term of x cube. Then I'll ask only x minus 12x plus 9x, that will be equal to minus 3x. Okay, now let's rearrange. It will be x raised to 4, then the power 3 minus 6x cube power 2 plus 10x square power 1 minus 3x plus 0. Okay, so this is your answer. Note down question number 3rd. Okay, now let's move to the next one. Question number 4. Show that the function R2 x belong to R such that minus 1 is less than x is less than 1. Okay, so the domain is R and codomain, you can say this as open interval minus 1 to 1. Okay, defined by fx is equal to x upon 1 plus modulus of x. You have to show this is 1 1 and on. Okay, so let's start first for 1 1. Okay, now for 1 1 again there will be three cases. Okay, because sorry, two cases here, it is again modulus, so x can be greater than 0 or x can be less than 0. So case 1, x is greater than equal to 0. Okay, let f of x1 equal to f of x2. So what does that imply? X upon 1, x1 upon 1 plus x1, because see, 1 plus x1, it is greater than 0, so modulus of x will be equal to modulus of x. This is equal to x2 upon 1 plus x2. So I'll cross multiply x1, I'm sorry, I'll cross multiply with this. x1 into 1, x1 plus x1, x2. Similarly here, x2 into 1, x2 plus x1, x2. x1, x2 gets cancelled. That implies x1 equal to x2. Okay, so it's 1 1 for this case 1. Let's take case 2. X is less than 0. Now let f of x1 equal to f of x2. So what does that imply? x1 upon 1 minus x1. Reason x is less than 0, that means modulus of x will be equal to minus x. And here x2 will be equal to 1 minus x2. Cross multiply x1 minus x1 x2 equal to x2 minus x1 x2. Here also it gets cancelled. That implies x1 equal to x2. So for both the cases, I can write down f is 1 1. Clear? Now let's see for onto. Now see, the domain here is from -1 to 1. Sorry, codomain. So I can take the value of y which belongs to codomain such that either it is negative or positive. Means greater than negative greater than -1 and positive less than 1. So here I can take case 1. Let 0, sorry, not 0, -1 less than y less than 0. Clear? So in this case, we will take fx is equal to y, right? So x upon 1 plus modulus of x is equal to y. Now see here, y is negative. Clear? Y here is negative. So in this condition, the denominator will be always positive. Here you will see that this denominator will be always positive because 1 plus modulus, so that will be also positive. So denominator is positive. So now here y is negative. So what does that imply? Okay, here y is negative. Alright, y is negative. That implies x must be also negative. Okay, then only it is possible. So that implies modulus of x is equal to minus x. Okay, so now what I will get? X upon 1 minus x equal to y. So x equal to y minus yx. Okay, so I'll carry it forward. So x plus yx, that is equal to y, x common, 1 plus y equal to y. X is equal to y upon 1 plus y. Okay, in this case I will take fx equal to f of y upon 1 plus y. Clear? So this will be equal to this x, so y upon 1 plus y upon 1 plus modulus of y upon 1 plus y. Clear? So when I will solve this, I will get f of x equal to y upon 1 plus y. Now see, here it is modulus 1 plus y, and the value of y is from -1 to 0. Clear? So when I will do y plus y, that will be positive. Clear? That will be equal to positive. Okay, but numerator y is negative. So I will get 1 minus y upon 1 plus y. Okay, here denominator is positive, numerator is negative. So when I will remove modulus, it will be minus. So y upon I will multiply here. Say LCM 1 plus y will get cancelled. 1 minus y plus y, that is equal to y. Okay, y gets cancelled. So I got fx equal to y. Clear? For which case? For minus 1 less than y less than equal to 0. Clear? Now similarly, when I will take the other case for onto, okay, I will take case 2 for onto. That will be equal to 0 less than equal to y less than equal to 1. So here when I will take fx equal to y, that means x upon 1 plus modulus of x equal to y. So what happened in this case? Y is positive. That means denominator is always positive. So numerator will be also positive. Therefore modulus of x will be equal to plus x. Okay. So when I will see here, this will I will get x upon 1 plus x equal to y. X is equal to y plus xy, x minus xy equal to y, x common 1 minus y equal to y. So what does this imply? Let me write it down this stuff here. X into 1 minus y equal to y, x equal to y upon 1 minus y. Okay, so now when I will put fx, I will get f of y upon 1 minus y. Okay, so this will be equal to fx equal to x, that is y upon 1 minus y upon 1 minus modulus of y upon 1 minus y. Now y is positive, okay, and it is less than 1, so 1 minus y is also positive. So I'll remove modulus, its sign will not change. Here, okay, sorry, it's 1 plus, not minus. 1 plus, its sign will not change. So this will be equal to y upon 1 plus y cancel, 1 minus y plus y, and that will be equal to y. Here also I got in case to fx equal to y, right? So for every y belonging to codomain, there exists x belonging to domain. What is the domain? R, such that fx is equal to y. Therefore f is onto function. Here, hence we have proved that f is onto and f is also 1 function. Okay, so now note down question number 4. So we have proved here first, case 1 is here and case 2 is here for all. Okay, now let's move to the next one. That is question number 5. Question 5, show that the function f r to r given by function fx equal to x cube is injective. Injective means 1 1. Okay, so now it's a simple sum. Let fx1 equal to fx2. So what does that imply? X1 cube equal to x2 cube. See, when we take cube root, this will be x1 equal to x2. If it was square, then this will not be the situation. If it was square, then x1 will be equal to plus minus x2. But here it's cube. We know that the cube of negative number is negative and the cube of positive number is positive. So here we get x1 equal to x2. Okay, we started with fx1 equal to fx2. and we proved x1 equal to x2, therefore f is 1 1, or I can say injective. Here, so this was about question number 5, just note it down. Okay students, so that's it for today. In our next video lecture, we'll continue with question number 6. Thank you.